Welcome to today's deep dive. Our mission today is extracting the most fascinating insights from a really comprehensive source on European inland navigation.
Yeah, it really is a brilliant document. It kind of strips away that romanticized image you might have of lazily floating down a river and reveals the hard science and the intense pressure behind the profession.
Okay, let's unpack this because we are talking about massive rivers here, like the Rhine or the Wall, and the source notes the currents there can hit up to 10 kilometers per hour, which seems incredibly fast for a massive cargo ship to deal with.
It is, and it completely reframes how we think about a ship's engine. I mean, that horsepower isn't there just to save fuel or get to port faster. It is a strict vital safety requirement.
So a captain needs that raw power just to overpower the water.
Right, just to maintain basic steering control. Basically, a modern captain has to act as a hydrodynamic physicist.
How so? Like dealing with the flow around river bends.
Precisely. Take a river bend. The physics are highly asymmetric depending on the weight of the vessel.
Oh, because of how high it sits in the water.
Exactly. If a ship is empty, it sits high. That means the wind and the fast surface currents will just shove it right into the fast-flowing outer curve of the bend.
But if a ship is heavily loaded,
Then its hull sits deep in the water. Down there, it hits colliding undercurrents water bouncing off the riverbank, which actually pushes the heavy ship away from that outer bend.
here's where it gets really interesting. Because you'd think moving from a wild river to a perfectly straight, restricted canal would make things easier. But the physics change entirely.
What's fascinating here is a terrifying phenomenon called the bank effect. This relies on Bernoulli's principle. Think of it like this. When a massive ship travels down a narrow canal, it squeezes the water between its hull and the canal wall.
And to get past the ship, that squeezed water has to speed up, which in physics means faster-moving fluids create lower pressure, right?
Correct. That fast-moving water essentially creates a vacuum along the side of the ship.
So this low pressure creates a powerful suction that pulls the back of the ship, the stern, directly toward the canal wall.
Yes.
Wait, so if a captain feels the stern being pulled toward the right bank, their instinct would naturally be to steer hard to the left. Does that work?
Counterintuitively, it's the worst thing they could do.
Really?
Turning away from the bank exposes the side of the hull, forcing water to rush even faster through that narrow gap.
Right.
That drops the pressure even further and sucks the ship into the wall even harder.
Wow. So what is the remedy to prevent the front of the ship from swinging wildly into oncoming traffic?
You have to immediately drop speed. That is the only way to restore the hydrodynamic balance.
Incredible. So we've navigated the tricky river bends and survived the narrow canals, but eventually these ships have to reach the sea. That brings us to the locks, like the massive ones at I.J. Moyden. I saw the source mention a saltwater trap there.
It comes down to density. Saltwater is heavier and denser than freshwater. Imagine a thick, heavy fog rolling into a room, it immediately sinks to the floor.
And the same thing happens when those lock doors open to the ocean. The heavy saltwater violently rushes into the lock underneath the lighter freshwater.
Exactly. It creates a massive, invisible subsurface current that essentially grabs the ship from behind. The crew actually has to secure the back of the vessel first, just to keep from being shoved forward into the lock doors.
The source mentions some serious hardware designed to fight these invisible forces, things like flap rudders and Veth jets.
Those give the captain a major edge. Flap rudders have a hinged tail that can bend up to 100 degrees, which directs the water sideways to generate massive turning force.
And those Veth jet bow thrusters essentially suck water from underneath the hull and shoot it out in a full 360-degree circle to push the front of the ship in any direction.
That is some serious engineering. But if we connect this to the bigger picture, all this technology ultimately serves human decision-making, which raises an important question. What happens when standard traffic rules aren't enough to keep a ship safe in these extreme conditions?
Right. The source brings up a fascinating piece of maritime law called the Good Seamanship Rule, or Article 1.05.
Basically, if following standard navigation rules is going to cause a crash because of these wild fluid dynamics,
A captain is legally mandated to break the rules to save the ship.
yes, the ultimate responsibility rests entirely on their split-second judgment.
So what does this all mean for you? It means that navigating these inland waterways isn't just about casually turning a steering wheel. It is an intense, high-stakes chess game played against fluid dynamics, extreme weather, and heavy traffic.
The next time you see a barge peacefully gliding down a canal, you will understand the invisible, incredibly complex forces that the crew is actively battling to safely deliver the goods that keep society running.
Beautifully said. And I want to leave you with one final provocative thought to ponder, based on the sources section on alternative fuels. If the emission-free future of this industry relies on hydrogen fuel, which must be stored in massive, incredibly heavy, high-pressure cylinders that eat up precious cargo capacity, how will this massive shift in weight distribution fundamentally rewrite the delicate hydrodynamic balance and hull speed limits we just explored? Thanks for joining us on this deep dive.